Good morning, everybody. Thank you for joining us for another webinar for Dolomite Microfluidics. My name is Ben Knappett. I'm a senior scientist here working in Dolomite. And today we're going to talk about how to choose optimal chemicals for microencapsulation. Specifically, we're going to focus on emulsion stabilizers for this talk. So we will talk about what emulsion stabilizers are, and then we're going to move on to the different types of emulsion stabilizer that are available to choose from. And then subsequently how to go about making a choice as to what emulsion stabilizer might be the best suited for your application. And then we'll look at a couple of example applications to just give an idea of how that all falls into place. Okay, so to start with, what is an emulsion stabilizer? Emulsion stabilizers are any material that lowers the interfacial tension between two immiscible fluids, and that enables an emulsion to persist without the droplets coalescing or breaking apart. Ideally, we want that emulsion to be nice and monodispersed when working with microfluidics, so any coalescence events become very noticeable, so it's important to try and minimize those as best as possible. Examples of some emulsions in day-to-day life are things like soap bubbles and mayonnaise. Soap bubbles are gas in water emulsion, mayonnaise is an oil in water, as is a salad dressing. Things like a salad dressing, being an oil and water emulsion, aren't particularly stable. The emulsion stabilizers aren't very effective, so you have to keep shaking them to maintain that emulsion. So that's an example of a not particularly brilliant emulsion stabilizer. And things like margarine are a water in oil emulsion, which is why after a little bit of time in the fridge, you sometimes find a little bit of water sitting on the top of your margarine. For microencapsulation purposes, the encapsulant, the API or nutraceutical, whatever it might be that you're trying to encapsulate within the droplet, will need to be dispersed in the droplet phase. And you will then require a suitable emulsion stabilizer to form either the liquid emulsion, if that's the final intended use, or to cure those droplets into hard beads to form a capsule. So what do emulsion stabilizers typically look like? General term covering emulsion stabilizers is also just the term surfactant. You hear the two used fairly interchangeably, surfactant being short for surface active agent. They typically are defined as having a hydrophilic head group and a hydrophobic or lipophilic tail. This enables the molecule to sit at the interface between the oil and water, or the two different phases that you happen to be emulsifying, and lower that interfacial tension to allow it to be stable and maintain its structure. That can include things like liquid-solid interfaces as well. So surfactants are commonly used for nanoparticle synthesis as well. So compounds like oleic acid or olalamine are frequently used to stabilize metal nanoparticles as they nucleate and grow from organic solvents such as octadecene. Typically, surfactants are simple molecular structures, but there are a range of different types, as I will discuss now. So firstly, in terms of the phases that you can have within your emulsion, most liquid-liquid emulsions are comprised of an oil phase and a water phase. Particularly those in nature are a water phase and typically a hydrocarbon oil. In addition to aqueous phases and hydrocarbon oil phases, in scientific activities, we quite often use two others. We use fluorocarbon oils, which are particularly handy in biological applications because the fluorocarbon phase is non-miscible with both aqueous and hydrocarbon materials. So when encapsulating materials that have ambiophilic properties, that's actually quite useful to prevent anything from seeping into the continuous phase. The other is silicon oil. This is used a little less frequently in some of our microfluidic applications, but is used quite extensively in things like the cosmetic industry to add texture and feel to things like skin creams and topical treatments, and to allow the release of material in skin creams. For each of these combinations of different phases, you will need a different stabilizer that is tailored to have components that are favorable to exist in each of the two phases. You can see in the diagram there examples of an oil in water emulsion and also a water in oil emulsion. Okay, so what are the different types of stabilizer that you could opt to choose from? So as I mentioned already, there are quite common simple molecular surfactants. These are typically relatively low molecular mass compounds which have a carboxylic acid group or sulfonate group at one end, and a longer hydrocarbon chain. Depending on the length of the hydrocarbon chain, you can affect how it stabilizes different emulsions. I'll talk a little bit about that in a moment. Moving on from the simple molecular, you can also have polymeric stabilizers. So polymers tend to have a hydrocarbon backbone, and then the side groups coming off of that polymer can be hydrophilic or can be tuned to the particular materials you're trying to stabilize. Block copolymers are also quite effective for this. You can see on the diagram there on the top right, the blue and red block copolymer and how that will sit at an interface to direct the hydrophilic component in one direction and the hydrophobic component in the other direction. As well as something being either molecular or polymeric, you can have either non-ionic or ionic surfactants. I'll talk a little bit in a moment about how those act differently for certain applications, but straightforward long-chain carboxylic acid groups are non-ionic, and there are a number of different ionic, either cationic or zwitterionic, and anionic stabilizers that can be used as well. And the final group that we'll discuss a little later is using nanoparticles to stabilize emulsions. These are called Pickering emulsions, which are starting to find more and more applications in industry. So here are just a few examples of some of the structures for the stabilizers we've discussed. So sodium dodecyl sulfate is a very common ionic surfactant. So you can see that it's a salt of sodium, and it has a long hydrocarbon chain and then a sulfate group on one end. And it's particularly good at stabilizing things like gas in water emulsions. It's a very foamy stabilizer. Oleic acid is an example, as I mentioned, used for nanoparticle synthesis quite frequently. Simply a simple molecule with a carboxylic acid group at one end, and again, a longer hydrocarbon chain, this time with a double bond halfway through. Tween and span are both non-ionic surfactants of a sorbitan class. I'll discuss the comparison between those two a little later because they do come up quite frequently, and sometimes the nomenclature can be a little confusing. So we'll discuss those in a bit more detail. Polyvinyl pyrrolidone is a commonly used polymeric stabilizer, and fluorophase is a stabilizer that we actually manufacture ourselves here at Dolomites. It's an example of a Pickering emulsion, so it is a silica nanoparticle, which is surface functionalized with the pre-existing OH groups that you normally find on a silica nanoparticle, but also with some fluorocarbon chains, which enable it to stabilize water in fluorocarbon oil emulsions. Okay, so those are the options. How do we know which stabilizer we're going to choose for a given application? So let's look at some of those in a little bit more detail. Firstly, something to note is a factor called the Hydrophilic-lipophilic Balance, or HLB. This is a commonly used measurement of how hydrophilic or hydrophobic or lipophilic a compound is. It's measured by the molecular mass difference of the hydrophilic and lipophilic components of the molecule. So you divide the hydrophilic by the lipophilic mass, and then multiplied by, I think, 20. There's a multiplier effect. That gives you a unitless value. If that value is greater than 10, you consider this to have a high hydrophilic-lipophilic balance, which would suggest that overall that molecule is hydrophilic and would likely stabilize oil and water emulsions. On the other side of things, at the low end, if you have a less than 10 for your HLB, that would suggest overall you have lipophilic behavior and that you would stabilize a water in oil emulsion. You can see there's a little diagram at the top right there, which gives you a scale from 0 to 18, along with some of the common characteristics of stabilizers with that hydrophilic-lipophilic balance. So at the top, you have sort of solubilizing agents and detergents that are very hydrophilic. And at the bottom, things like anti-foaming agents are quite hydrophobic and therefore tend not to stabilize gas bowls in water. Another useful thing about HLB is it acts as an indicator of which of the two phases you would like to disperse your stabilizer in to begin with. So obviously, if it's more lipophilic, that would tend to suggest you want to disperse it in the lipophilic phase. It is only an indicator, though, of performance. It will tell you information about the surfactant itself, but there are two components to consider. One is the surfactant you're using, and the other is the interface that you're trying to stabilize. And so it gives you information on one but not the other. So it's a useful guide, but there's no guarantee that a surfactant will perform brilliantly in a particular circumstance. Conveniently, some of the websites offering chemicals will grade surfactants by a hydrophilic-lipophilic balance. So you're able to see if you want to pick something that has a particularly high or low lipophilic balance, you can look at the different stabilizers that are in those ranges. So it's useful to take into account, but not necessarily to rely solely on. Similarly, factors such as the critical micelle concentration, or CMC, are equally indicators of how effective a stabilizer might be, but not necessarily any guarantee. Okay, so one of the choices we have is whether we use an ionic or a non-ionic surfactant. So the non-ionic surfactants obviously have no formal charge on them. They come across a range of different HLBs, so depending on how they're functionalized and what the structures are. Typically, they're biologically friendly, and that means that they're very commonly used in the food and cosmetics industries. And so materials such as SPAN and Tween and Tritium X100 are fairly common non-ionic stabilizers that are found in a large number of products. Anionic surfactants, on the other hand, tend to contain either a sulfonate or carboxylate or phosphate head group with a long hydrocarbon tail. Typically, they are high in their hydrophilic balance, simply because the charge is very preferably solvated in polar solvents. This class of surfactants includes stearates, which comprise a significant portion of global surfactant usage in detergents and soaps. Something like 50% of global surfactant use is in the stearates category. So yes, they're very commonly found in household detergents, shampoos, conditioners, and the like. Their performance is affected by a couple of factors. So obviously pH. Depending on the pH of the solution, you might protonate or deprotonate your surfactant, which might exacerbate its charge or reduce its charge. So you can protonate an anionic surfactant by decreasing the pH sufficiently, and that will obviously change its properties slightly. The other thing is temperature can affect this, so their solubility will slightly decrease as temperature increases because you destabilize the charge group. Cationic surfactants, on the other hand, tend to have an ammonium head group. They have mid to high lipophilic balances because the ammonium group has functional groups coming off of it, and so it's a bit easier to shield that positive charge by putting maybe more lipophilic groups on that quaternary ammonium ion. They are used very frequently in things like antimicrobial or antifungal products, specifically because the cations tend to disrupt cell membranes of bacteria and viruses. On the flip side, that might suggest that the use of a cationic surfactant might not be a great idea if what you're looking to encapsulate is biological material, because you run the risk of disrupting that material once you do your encapsulation. I mentioned before SPAN and Tween, so these are non-ionic stabilizers used very commonly. I thought I'd briefly touch on these just to give an idea of the structures and what they're used for. So they are trademarked materials, and there are a range of sorbitan esters and ethoxylated sorbitan esters, respectively. They have a number following their name, so Tween 20, Tween 60, SPAN 80. The number denotes a specific hydrophobic tail group. So that in turn then affects the hydrophilic-lipophilic balance. So across that range of numbers, there's a range of different HLBs that you can use. So essentially, you can tune your Tween or SPAN to best suit your emulsion. For instance, Tween 60 has a monostearate tail group, whereas Tween 80 has a monooleate tail group, and that's what you can see in the bottom left image there. It's Tween 80. There are also in between the 10s, there are numbers ending in 5, so 65 and 85. These are functionalized with 3 of the hydrophilic tail groups, so that obviously quite significantly shifts the hydrophilic-lipophilic balance by putting a lot more lipophilic material in the compound. So the numbers don't quite go up in order. The intermittent 5s have a higher hydrophilic-lipophilic balance. It's not quite a linear scale, so it's worth just checking what the functional groups are before you use them. They're very popular due to the fact that they are generally regarded as safe, they're FDA approved, so very low cost, and are found in a very large number of food and cosmetic products. They are good for general purpose stabilization, but in typical high-performance applications like we focus on with microfluidics, they are often a useful starting point to figure out what sort of hydrophilic balance you might need or what emulsion stabilizer will work. But I would say you can typically improve upon their performance with a more specified or high-performance stabilizer. One of the other options we could choose between is whether or not we use a polymer versus a simple molecular surfactant. So the way that polymers stabilize the interface is they're much larger molecules that would tend to wrap around the droplet surface, particularly the component which favorably interacts with whatever the droplet phase is will stick to the surface of the droplet. They're very flexible in terms of their composition, particularly if you're able to make your own polymers or block copolymers to stabilize your emulsions. You can completely tune the different weights of the different blocks of the copolymer, the frequency of the blocks, various things like that. So they're very, very customizable. And so you can tune them for a specific type of emulsion to try and really, really optimize the stability you get. Because they're bigger, bulkier molecules, they're a little bit slower to diffuse to interfaces. So depending on the total molecular weight, you might want to consider that it'll be slower to stabilize interface, which might affect things like your droplet production rate. And they can also be harder to remove once bound. So they have lots of individual binding sites around the droplet, and therefore washing them off can sometimes be more challenging. That doesn't mean to say you can't wash them off at all. It might just take a little more effort. They can also change the rheological properties of the fluid, so that sometimes they're used simply as viscosifiers without significant interaction with the droplets present. So it's worth considering whether or not the change in viscosity or rheology is a change you want to introduce or not. Also, their behavior is less easily predicted by HLB. That's better suited for small molecular stabilizers. So just be wary of HLB numbers quoted for things like block copolymers. You can see in the diagram on the side there, we have a different block copolymer with PEG and PLA. And from the top down to the bottom, we are keeping the PEG quantities the same, but we are increasing the molecular weight of PLA that we're putting in. And so you can see that the PLA is spreading across the surface of the interface. So each of those molecules takes up more and more space the more you increase the proportion of the amount favorable for your droplet phase. So you'll have fewer and fewer polymeric molecules at that surface. One of the other options is Pickering emulsions. I mentioned earlier they're finding more and more applications. So these are interfaces that are stabilized by particles rather than molecular stabilizers or polymers. Again, like block copolymers, you can very flexibly control the properties of these particles during synthesis to influence their emulsion stabilization behavior. You can make them different sizes, you can put different functional groups on them, make them out of different materials in the first instance. Things like silica and titania are quite commonly used. The resulting interface is expanded into 3 dimensions. So rather than being a very, very thin 2-dimensional layer, you add some thickness to the interface. The advantage of that can be that you can control the transit of molecules between the droplet phase and the continuous phase. So a couple of examples of how you might use this. Firstly, you could make that layer not too thick, but just thin enough that you can allow some drug to transition through from your droplet to your continuous phase. So if you wanted to have a sustained drug release from an emulsion in, say, a topical skin treatment, you can use something like a Pickering emulsion to slow down the release of the compound from the inside of the droplet. Or we could go for a really thick boundary and really prevent any molecules transitioning to and fro. And that can be used to prevent what we call crosstalk between droplets in instances where what's contained within the different droplets is important to isolate in some biological applications I'll talk about a little bit later. Some disadvantages might include the fact that they are a little bit newer to the market. There may be some regulatory concerns over the fact that you're using nanoparticulate material in the stabilizer, and also industrial scale-up of manufacture for nanoparticles is a little bit less well explored than, say, large-scale polymer manufacturing or small molecule designs. So lastly, one option to consider is that you might not find the perfect stabilizer for your system as a single component. You might need to add multiple components to really optimize the stabilization. in a lot of commercial products on the market, for instance, soaps and detergents, when you're forming emulsions with these materials, you don't really know which oils or dirt you're going to encounter and need to form droplets from, and therefore a slightly scattergun approach of having a range of different hydrophilic-lipophilic balances and different types of foaming or non-foaming surfactants can help to tackle whatever oil needs to be emulsified. In the case of microfluidics applications, it's a little less common that you would have unpredictable compositions of your droplets, but at the same time, even for a known composition, you might still find that having more than one approach to stabilizing that interface is effective. Okay, so let's just go over lastly a couple of examples in microfluidics of how we might choose an emulsion stabilizer. So firstly, we'll look at the encapsulation of biological material such as cells or proteins. The droplet must be aqueous, of course, to support that biological media. And typically, our continuous phase would be fluorinated because there are no fluorinated compounds in biology, and therefore it enables us to encapsulate proteins which might have some hydrophilic or some hydrophobic properties. If you just used an oil, it might be possible for those molecules to solvate into the continuous phase, which is not ideal. Depending on what your application is, there are a couple of different options for how you might stabilize this emulsion. For things like single-cell analysis, it can be really important to prevent droplet-droplet crosstalk. If you're trying to isolate individual cells and understand them in isolation from one another, the last thing you want is after you've lysed them for the proteins to start transferring between the droplets via the continuous phase. So in this instance, Pickering emulsions, as discussed, create a nice strong barrier to prevent molecules from entering or leaving the droplets, which can be really useful. On the other hand, if you're looking to do droplet PCR, you're going to need to heat cycle the emulsion, and so thermal stability for that emulsion is rather key. In which case, using a non-ionic molecular or polymeric surfactant may offer higher stability during PCR cycling. It may require testing both to see which is ideal, or potentially even trying a combination of factors to see which works the best. Okay, so another example of application would be the encapsulation of APIs in PLGA particles via a DCM in water emulsion. This is something we've done a couple of webinars on before. The process itself is solvent extraction driven. So you need to be able to release that DCM solvent from the droplets, and that means that as you dry out the droplets, they will shrink and change in size. So typically, we tend to use polymeric or molecular surfactants in this case, rather than, say, Pickering emulsion, which changes size less easily. So you need a flexible stabilizer or combination of stabilizers. It's also important to consider the nature of the API itself, because you want to avoid the API from leaching into the continuous phase. So for instance, if you have an API that has some polar properties or hydrophilic properties, you might find that leaches out into the aqueous phase as the droplets are drying. And so one approach to prevent this might be to use multiple emulsions or double emulsion, in which case it's worth factoring in that you have two interfaces that need stabilizing. You have first the water in oil interface and then the oil and water interface. It can be the same stabilizer, or you might find that different stabilizers work best for each interface depending on the composition. You also need to be able to stabilize both the initial liquid droplet and also the solid bead that then results. And you might also want to be able to wash that stabilizer from the PLGA after drying. So we factored all of this into account here at Dolomite, and we produce a stabilizer called Aquaphase, and that's optimized for stabilizing exactly this type of droplet. And the approach we took was to use a proprietary blend of polymeric stabilizers. Okay, so the last example I want to discuss is the introduction of gas bubbles to a neutral buoyancy, or to reduce fat content, for instance, in things like oil and water emulsion food products. Gas bubbles are typically stabilized most effectively by higher HLB surfactants. As you noticed from the chart earlier, the lower HLB stabilizers are used as anti-foaming agents, and obviously what we want to sustain here is foam. And so you tend to find that the gas is relatively hydrophobic, and therefore typical detergents such as SDS are ideal for a gas in water emulsion. So if you have gas in water in oil, SDS is useful for stabilizing that internal emulsion. For a gas in oil emulsion, both the gas and the oil are relatively hydrophobic, and so you tend to find that those standard foaming agents don't work so well. Which in this instance, actually, there's some interesting research papers looking at the use of Pickering emulsions to stabilize emulsion formation with a gas in an oil droplet, and that can be as simple as using a surfactant which crystallizes onto the surface of the interface. So you have an almost liquid crystal type stabilizer that sort of bridges the gap between a normal stabilizer and a Pickering emulsion. Yeah. Okay, so in summary, there are quite a lot of emulsion stabilizers you can choose from of various different types and compositions and structures. Understanding the way that these different types of stabilizer will function will help to guide your choice. There are a number of indicators you can use, for instance, HLB or critical mean cell concentration. These are a useful guide, but they're not absolute. So they're worth taking into consideration, but be aware you'll need to trial a couple of surfactants to find something that works ideally for you. It's also useful to be aware of other application areas that are having to stabilize similar types of emulsion. So if you're looking to stabilize water and fluorinated oil droplets, look to biology and see what people have been doing in that area. If you're looking for oil and water or silicon in oil, then maybe look to cosmetics and see what can be found out from this. And also just to consider using blends of stabilizers. Sometimes you find that multiple stabilizers working together can be more effective than one on their own. Okay, thank you very much for listening. We're now going to go to our live web Q&A, where we'll be around to answer your questions for the next 20 minutes or so.